Alright, we are on the last chapter.
That's why they said you were laughing.
Okay.
Pointing at you from before and laughing.
So this last chapter we're covering is not multivariable calculus.
Let's go.
Huh?
It's proofs. Because if you're going to go on to study mathematics in college, then you're going to have to do proofs.
All of it here.
Oh, so it's like beyond multi?
Yeah, nothing.
Yeah, like higher level mathematics.
Bruh, that's great.
And depending on the professor you get, maybe your professor is heavy into proofs, and maybe your professor just wants to show you, like, your professor wants to just want you to do like the applications of it. Yeah.
Do we take multivariable then?
Yeah, you don't get credit for this. There would need to be an AP exam for this then, but there is none. Okay, so there's three different kinds of proofs. Got deductive proof, indirect proof. Remember we did a little of that in PCH when we did logic? Remember the indirect proof?
Yes.
Apparently not. And then proof by mathematical induction. So we're just going to do one at a time. So first, deductive proof. Now, most of these proofs are from number theory. Number theory is the study of the integers, yeah? So, look at the four definitions, and using these four definitions, we're going to prove other things from it. Some are easy, some are more difficult. So the first definition, A is even if and only if, notice that phrase from logic? So normally in definitions, that's where you would see the phrase if and only if, yeah? A is even if and only if A is equal to 2k for some integer k. And you know, you guys know what if and only if means, right? Do we need to discuss that? P, if and only if Q, means P implies Q and Q implies P. That means you can go either direction, yeah? Okay, so according to the definition, is 6 an even number?
Yes.
Why?
Divide by 2.
No, the definition. Because it's equal to 2 times an integer, and that integer is 3. See, that you have to understand the definition if you're going to use it. Is 0 an even number?
Yes.
Yes. Why? Because it's 2 times an integer. And what is the integer?
0.
That's right. Is negative 8 an integer?
Yes.
Yes, because it's equal to 2 times an integer, and that integer is negative 4. That's the definition. Okay, B. A is odd if and only if A is equal to 2k plus 1 for some integer k. So is 5 an odd number?
Yes.
Why?
2 times 2 plus 1.
There you go, now you're getting the hang of it. Because it's equal to 2 times 2 plus 1. Is negative 7 an integer?
Yes.
Yes, because it's equal to 2 times something plus 1. And what is that something?
Negative 4.
There you
Oh
go.
my god. Look at me. So funny.
Right, because if you go to lower school and you ask like a 4th grader, is 8 even? And they're going to say, yeah. Okay, and then you ask them why. What do you think they're going to say? Yeah, because it is, right? Okay, what about this next one? A divides B. That's the way we say it. A divides B. Or another way you can think of it is A is a factor of B. Okay, but most number theory people, they will just tell you A divides B if and only if, what? B is equal to AK for some integer k. That's the way we would symbolize it, like that, yeah? You guys remember all the symbols from logic?
Yes.
So if and only if is the biconditional, yeah? So A is a factor of B if and only if B is equal to AK for some integer k. See, k is an element of the set of the integers. Remember, capital Z is the integers. Okay, so let me ask you this question. Is 3 a factor of 12?
Yes.
Or 3 divides 12? Yes. Why?
1/4.
No, I didn't. No, you gotta refer to the definition.
Oh,
Okay, are you paying attention even here? Or are you in your own world here?
That's what 12 is.
Yes, because 12 is equal to
3 times
3 times some integer,
4.
which is 4.
Oh,
I think we gotta do another one.
Oh, he did 3.
Does 5 divide 30? Yes, because 30 is equal to 5 times some integer, and that integer would be 6. This is pretty central in number theory. And then the last one, have you guys seen that notation before? Some of you program computers? You guys use the mod thing? A is congruent to B modulo M. That's the way you say this. A is congruent to B modulo M if and only if, I guess we gotta write it because I don't want to go on this side of the board, if M divides A minus B. Okay, so let me ask you this. Is 7 congruent to 1 modulo 3?
Yes.
Yes, why? Because 3 divides 7 minus 1. 3 is a factor of 6, that's why, yeah? Another way to think of this is 7 and 1 have the same remainder when you divide it by 3. Whoa, that's another way to think about it. Right? Because if you divide this by 3, you get 1 remainder, right? You divide this by 3, you get 1 remainder. So that's another way to think about it. Okay, so using these definitions, we're going to prove some things. Now, I'm going to do 3 of them on the board now. And I did all of them. There's no video for this. There's just like a written solution. So I did them all already. It's on the Google Drive. So deductive proof is you start with a statement and then you just like write another statement that follows from it, right? And you keep on doing that until you get to your whatever the result is. Oh, before we even go on anymore, do you guys know what closure is? Closure, there you go. Like, is the set of integers closed under addition?
Yeah.
Well, first of all, you gotta understand what closed is. Okay, so the set of integers is closed under addition because if you add any 2 integers, you will get another integer. What about subtraction?
Yes.
Is the set of integers closed under subtraction? If you subtract any 2 integers, will you get another integer?
Yeah.
What about multiplication?
Yeah.
Yes. You multiply any 2 integers, you will get another integer. What about division?
No.
No. And what's the counterexample for that?
3 divided by 2.
What?
3 divided by 2.
Yeah, 3 divided by 2, or even 5 divided by 0, right? Those are not integers. Okay, so the set of integers is closed under addition, subtraction, and multiplication. Okay, that's important too. Okay, so here we go. Shall we do number 1?
Yeah.
Well, number 1 and number 2, 1 through 4 are pretty darn easy. Okay, let's just do 4 then. Okay, we want to prove that if A is odd, let's do it this way. If A is odd, then, what does it say? A squared is odd. Because can you do this as a proof? Oh, 1 is odd, and 1 squared is odd. 3 is odd, so 3 squared is odd. Therefore, it works for all integers. No, you have to prove it, right, for everything, right? So that's why we're going to use deductive proof. So what we need to show is if this is true, then this will have to be true as well. So if A is odd, what can we say? What is the definition of an odd number?
2k plus 1.
A is equal to 2k plus 1 for some integer k. You have to state this now. Why do you have to state this? Exactly, because k, what if k was like radical 3? Or 1/2, right? It's not going to work. So this is really important. You have to say that k is an integer. Okay, now we want to prove something about a squared, so obviously, what do you think I'm going to do to both sides of this equation? I'm gonna square both sides. So a squared is equal to 2k plus 1 squared, which of course is equal to, maybe we'll do this then, 4k squared plus 4k plus 1. Now, in order to prove that something is odd, you have to show that it's equal to 2 times an integer plus 1, right? So can I write this as 2 times something plus 1? You bet your bippy. 2 times what plus 1? What do I need to put in the parentheses here? 2k squared plus 2k. Now, if k is an integer, can I say that this is an integer? Yeah, because again, it's closed under multiplication, and k squared is just repeated multiplication, right? And addition. So, like if you look at my written solution, it says since 2k squared plus 2k is an element of the integers, then you can say, then if a is odd, then a squared is odd. And that would complete the proof. And what do we do when we finish the proof? Quod erat demonstrandum.
That's it.
Exactly. You guys did that in MVC?
Yeah.
Quod erat demonstrandum. We did it with logic in DCH. Or when we did the trig proofs, remember? Or you can if you don't like Latin, then just go quite easily done. So that's what a typical deductive proof would look like. This is a simple one. Okay, now let's do which is the one we're going to use. We're going to use number 8 now. So I'm going to erase because we only can stay on this side of the board for the video. All right, so number 8. If A is congruent to B modulo M, and C is congruent to D modulo M, I guess we gotta do this then, yeah? Then A times C is congruent to B times D modulo M. Okay, this is what we need to prove. And then we're gonna actually use it to solve a problem, which will be on the test. All right, so what is the definition of A is congruent to B modulo M? M divides A minus B. And what about this? M divides C minus D. Now, what is the definition of M divides A minus B? A minus B is equal to M times some integer, yeah? So K. And C minus D is equal to M times some integer. Can I use K again? No, because it doesn't have to be that same integer, so you gotta come up with a different letter. I think I used J in the, when I did it, worked it out there. And then you have to say K and J are elements of the integers now. Okay, now what you have to do is you have to manipulate these equations so that we can get this. Now, if you ever get stuck in a deductive proof, what you can do is kind of work backwards. You can kind of cheat, yeah? Like this. So, you know the last step has to be A times C is congruent to B times D modulo M. Then what has to be the step before? Because otherwise, if you're going to go through the proof, you kind of have to have foresight. Hopefully by now you guys have some degree of foresight, yeah? If not, we just work backwards. Okay, so what has to be the step right before this? What's the definition of this? M divides AC minus BD, right? And then what has to be the step before this if M divides this? AC minus BD is equal to M times some integer. So we have to prove, we have to get to this step here. So how can I manipulate this equation and this equation here to get this? That's the hard part. Multiply the equations. So go this times this, and then this times this. Okay, so therefore A minus B times C minus D is equal to M times K times M times J. Okay, what would be the next step then? Multiplying this out, you would have AC minus AD minus BC plus BD is equal to, shall we just write M squared KJ then?
Never mind.
Okay, we got stuck here because look, this is AC plus BD. We need AC minus BD. Okay, so we got stuck, so erase. What's another thing I could do? So what's gonna happen on the test, usually I give like one problem from each section and then we have some applications of the thing too. So if I were to give one of these 8 problems on the test, probably would be this one.
Can you say D minus C equals MJ?
Yeah.
Oh, yeah? Oh, so that you can get the plus, that's why. Yeah, okay, you can do that as well.
Thinking something else.
Yeah. That would solve the problem, wouldn't it? Okay, but I'm thinking of something else. Or how about you guys come up with something else? Or shall we just use Kanashiro's?
No.
Then you can look at mine tonight to see what I did. Yeah, no, let's use Kanashiro's one. So this one here, then we can say that CD minus C is equal to M times some other integer. What letter do you want to use here?
Z.
What?
No, you don't want to use Z. Z is kind of, that's awkward.
Why?
Because, huh?
Why?
Okay, X, Y, and Z we don't want to really use because they're kind of reserved for other
D,
things.
F, B.
Okay, I think F would be a good one.
What?
F for some integer F then. Okay, now then what?
This is so long.
Now multiply it. So A minus B times D minus C is equal to MK times MF. Okay, multiply it out. AB minus AC minus BD plus BC.
AD.
What?
AD.
Where?
The first
Wait.
one.
Oh gosh, AD. You're right. E minus B.
BD.
Gosh, I screwed that one up, yeah? Is equal to M squared KF. So we got the A, where's AC?
We have
AD.
none
AD for the
The
beginning.
second one.
It's not
Oh,
AD
gosh. I screwed it all up, huh? AD
minus C.
minus AC, what's going on here? AC minus, okay, now it's correct. So I got the AD minus BD here, that means I have to move these two on this side, so AD minus BD is equal to,
Wait, what?
Wait, what?
Yeah, I
Doesn't
thought
make
it's
sense.
AC minus B.
oh yeah, we need what?
It doesn't work.
It doesn't work then.
Oh, because the sign changes together.
Yeah, okay, so this doesn't work either.
I thought you did like mine and then G and C and then you can.
Say that again?
Yeah.
Okay, so now we gotta come up with something else. Okay, I'll just tell you what I did on. I solved for A in this one. And I solved for C in this one.
Oh.
Oh.
And then now I multiply them. So A times C is equal to, okay, why don't we just do this in one fell swoop? What is this times that? BD, because then when you bring it over, then you get the minus, yeah? BD plus BMJ, I'm gonna do this one correct, plus CMK
What?
plus,
Oh, DMK.
Yeah, okay.
I said I was gonna do it correctly, plus M squared JK. Now did I do that correctly?
Yes.
Bring the BD over, so AC minus BD is equal to BMJ plus DMK plus M squared JK.
That's a code.
And then can I write this part here as M times something?
Yeah.
Yeah, so BJ plus DK plus MJK. And if all of these are integers, then is this whole thing here an integer? Yeah, because it's closed under multiplication and addition. And then this, so this follows from this, that follows from that. Therefore, we proved it quite easily done, or it wasn't really quite easy. Yeah,
So A, B, C, D is always assumed to be an integer?
yeah, these are all integers. Okay, now we're gonna use this to like do something. So this problem is gonna be on the test, but maybe I'm gonna give you more digits. Okay, find the last two digits of, okay, give me something. Give me a two-digit number.
28,
28, now give me another two-digit number.
48,
To the
47.
47th power.
Oh, no.
47.
Now, could you do this on your calculator? Like if I punch that in my calculator, can I just read off the last two digits?
No.
Clause is like E.
Yeah, because it's probably, this number is really big, so it'll probably give it to you in scientific notation. You won't? Yeah, but maybe your calculator, how many digits does your calculator give you? I know the TI-89 can go up to 200 digits, that's why.
What?
Oh, what? Oh, what?
Does anybody have a TI-89? Anyway, probably by the time we get to the test, I'll go 3 digits to the 3 digits.
All right.
And see how your multiplication skills are. Okay, so we're going to use the results of this theorem here. Do you guys know the difference between a theorem and a postulate or axiom? A postulate or an axiom is a statement that's so obvious it doesn't need a proof. A theorem is a statement that needs to be proven. Okay, so since we proved it, this is a theorem, so we're going to use this theorem. Now, how do I find the last two digits of 28 to the 47th power without a calculator? Well, what is 28 to the first power? 28. So would you agree that 28 to the first is congruent to 28 mod 10? Oh, sorry. If we want the last two digits to be the same, we gotta work in mod 100, right? Why mod 100? Because, okay, let me think of something. 647 is congruent to 347 mod 100. Why? Because what does this mean? 100 divides 647 minus 347, and what is this equal to? 300. 100 divides 300, right? So if you want the last two digits to be the same, you need to work in mod 100. If you want the last three digits to be the same, then what? Mod 1000 and so forth and so forth.
So
Yep.
why do you want two digits to be the same?
No, we gotta start somewhere. No, don't worry. Let's just go through this and see what we get. Okay, now, what about 28 squared? Okay, what is 28 squared? You guys should know your square numbers, right?
624.
What? No, time out. Because 25 squared is 625 already, right?
726.
No,
784.
780.
You can't use a calculator.
How do you do it?
Go like this, then 28 times 28. 4 carry 6, 6 carry 1, so 784.
See? Wait, what? What's 2? Oh, it's 2 20.
Oh, you can use the 20
Oh.
plus 8.
Or what, 30 minus 2 squared then?
Yeah.
Oh, yeah, okay, whatever, okay? Whatever arithmetic things that you have. Anyway, so would you agree that 28 squared is congruent to 84 mod 100?
Oh.
Right, because it's equal to 784, so therefore it has to be, the last two digits gotta be the same, right?
Yeah.
Okay, and then we keep on going, we keep on doing this until we can get up to 28 to the 47. We're gonna keep using this theorem repeatedly. Okay, so we could go 28 to the fourth power then, right? Isn't 28 to the fourth power gonna be this number squared then?
Yeah.
So 784 times 784. Or you're gonna cheat and use a calculator? Do you want me to let you use a calculator on this problem?
No, it's the 84.
5 6.
700 times
What?
84.
Wait, what?
6 carry 1, 3 carry 3.
Are we supposed to just do 82?
Say that again?
Just do 84.
How come it's going to be 84?
No, like.
There's still last two digits anyways, right?
So we only need to multiply 84 times 84 then.
That's what I want to do.
Okay, well, I don't know, maybe, well, let me see. So 2 carry 3, 7 carry 6, 8 carry 2, 8 carry 5, so
See?
6, 5.
Yeah.
Yeah, so you only need to multiply the last two digits. Yeah. It's congruent to 56 mod 100. Okay, now we need 28 to the 8 then. This is not equal, it's congruent. So basically it's this one squared then, right?
Yes.
Okay, so go 56 times 56 then, right?
Yes.
56 times 56, 6 carry 3, 0 carry, oh, that's it already, 36 already, yeah? 36 mod 100. Okay, then we square it again, so 28 to the 16th power is congruent to, so we gotta go 36 times 36, but that one we know, right?
Yeah.
36 squared, isn't that 1296?
Yes.
Yes.
Okay, so, okay, well, if you know it, mod 100. Okay, then 28 to the, now we're getting closer to 47. 32 is congruent to, okay, what is 96 times 96? 6 carry 3, 7, and 9 times 6 is 54. So 1/6 then?
Yes.
So 116 mod 100, yeah, we're getting there. Okay, now should I square this?
No.
No, because 64 is bigger than 47, so now you gotta figure out which ones can I multiply to get 28 to the 47, right? So I'm gonna obviously use this one, but if I use it with this one, that's 48.
8.
So this one and this one.
Oh, yeah.
This one, this one, this one, this one, this one, but then you gotta multiply lots of numbers though.
Wait, are you gonna show us the easy way now?
This is the easy way.
Oh.
Do those
Oh,
two?
there's a-
Which one?
Oh, wait. No, never mind.
Do 1, 2, 4, 8, right?
Okay, let's just start one. Okay, so if I do the, multiply these two, then you get 28, so these two, to the 40 is congruent to, so then you gotta multiply 36 times 16.
Alright.
6 carry 3, 6, 76? You guys are checking my work?
Yes.
Yes.
Okay, and then now, what do I wanna multiply this one by? I wanna get to 47, so this one times this one then?
Yeah.
So if I multiply these two, you get 28 to the 44 is congruent to, we gotta multiply 76 times 56, that's 76 times 56. 6 carry 3, I'm trying to concentrate here. 0, so 56?
Wait, can we just multiply by the 8 and divide by 28?
Oh, you can't do it, right?
Oh, I'm stupid.
And then, I'm trying to show you the way to do it here. Okay, then should I multiply this one times the 2 then?
Yeah.
So 28 to the 46 power is congruent to, gotta multiply 56 times 84 then. 84 times 56 is 4 carry 2, 0, 0, 4 then?
Yeah.
0, 4 mod 100. And then finally, multiply this one with that one, right? So 28 to the 47th power is congruent to, you gotta multiply 4 times 28. Down we can do in our head, right?
Yeah.
What?
1,
112, so 12. 12 modulo 100. So therefore, the last two digits of 28 to the 47 would be 1, 2. I think last year's test I gave a 3-digit number, but I think I should just stick to 2-digit number, yeah?
Yeah.
I'll give an easy 3 digits.
Oh.
Wait, give one that repeats.
Yeah.
Give one that repeats.
And I don't want to give you like 29 or 31, you know why? Because then you can use the binomial theorem, yeah?
Oh, yeah.
Like if I ask you to find the last two digits of like 29 to the 47 power, then you could just go 30 minus 1 to the 47 and just use the binomial theorem, right?
Yes,
We did this in PCH.
I remember that.
Or if I give you 31 to the 47, you can go 30 plus 1 to the 47. But I don't want you to use the binomial theorem. Maybe I should say use this theorem to find the last two digits. Okay, so we need a homework problem then. So give me a two-digit number.
11.
No, Song, you already gave that one.
30, 34.
Let's do an odd number since these are odd.
33,
33.
1,
31.
9.
30.
37. Oh, 37 to the 73.
Alright.
Okay, this is your homework problem. Homework. 37 to the 73. Find the last two digits.
Oh wait, that's our only homework?
No!
Anybody
You're gonna do those proofs, 1 through 8, but I did 2 of them for you. I did 4 and 8.
Anybody got a T on
I think, do you guys have that app? Somebody in my calculus class had this thing there, you take a picture of the problem and it solves it.
Photo man.
What is it called? Photo map?
Yeah.
You think it would work on this?
No.
Oh, I used to
doesn't
have
work
that
for-
app one time. Doesn't really
It doesn't work on word problems,
No,
huh?
it
Yeah, it
doesn't.
doesn't.
All right. Find the last two digits. So no, this plus the proofs, yeah. And then, do I see you tomorrow? Yes, then we do indirect proof. Tomorrow's homework is gonna be super easy because I think we're gonna do all of them in class, that's why. Because these are famous proofs. You know what the two most famous, I guess they're both in the top 10. There are infinitely many prime numbers. Have you ever seen the proof of that? No. And what about square root of 2 is irrational?
Yes.
Those are the two of the most famous proofs in mathematics. We'll do that tomorrow.
It's in my childhood.
In fact, one of the things, I hope, it depends how much time we have. You remember this? What is a 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared forever? This is an infinite series.
1 over k.
What?
Wow.
We did this in PCH.
E2.
No,
Pi squared
no.
over 6.
Thank you, pi squared over 6. We're actually gonna prove that if we have time.
Why are you so sick?
Oh,
Okay, I believe your calculator could do this if you punch in, because you have a sigma thing on your calculator, yeah?
no.
Anyway, if we have time, we're gonna prove it. I think Euler did this proof. Euler. All right, I just found the game on the internet, like where you guys are walking in the room. We'll play that and then we'll go home. What time does this class end? 12, yeah? Well, that took longer than I thought.